Welcome. This video covers abstract data types, which are abbreviated ADTs, and how they relate to the data structures that we'll be working with. First, let's understand what we're trying to do with this terminology. So the goal of this course in studying data structures is to design data structures. That's kind of the thing we're creating. We want to make them efficient. That's one of the major goals, is not just create a data structure that organizes information, but make it fast or otherwise efficient. And we analyze this in a scientific way. We don't just sort of like shout things, but instead we have data and evidence that we use to inform our decisions. We want these data structures to be universal, meaning that they could apply to pretty much any kind of computing environment. So I don't want to invent something that just works on, Linux in the year 2021 in C++ programming. Instead, we want these structures and designs to work on any kind of CPU chip, whether it's new or old, or fast or slow, and any operating system and any programming language. So we have to define what a data structure is in an abstract way. We can't be specific to any of those alternatives. And that means that coding doesn't work by itself. So if I want to say, here's what a linked list is, it's not sufficient to say, here's C++ code for a linked list or Java code or anything else, because that would not be universal to all of these other environments. So that's what we have an abstract data type for. Abstract data type has the acronym ADT, and we'll say that just because it's faster than pronouncing all of those words. So an ADT defines a structure's name. We give names to these structures, and that's actually pretty important. It's important to get the names right, to be clear. A description to say basically what it is, and then a list of operations, which are kind of like functions, and invariants, which are kind of rules that the data structure obeys. An operation is basically, you could think of it as a function. In object-oriented programming, it would be a member function usually. And an operation function, as with other functions, has a name, some input arguments, and an output return type, and a specification for what it does. So in the abstract data type, we've got a list of these operations, what their inputs and outputs are, and the purpose of them, what they do. We don't have code because we're not implementing right now. We're just specifying what is an array or a linked list or one of these structures. There also may be a list of invariants. Not all structures need them, but an invariant is a rule that the structure must always obey. And I'll say a little bit more about that in a moment, but it's basically for internal organization of the structure. And sometimes these invariants are phrased in terms of something a operation requires, a prerequisite to calling a function, or a invariant that an operation ensures, meaning something that the operation guarantees when it finishes. So a little bit more about operations. As stated a moment ago, a operation is a function. It's got inputs and outputs. We think of it as kind of an algorithm that does some computation on a data structure. And a ADT operation has a specification for what it does. There's maybe one way of breaking this up into kind of routine operations and more interesting ones. Pretty much every data structure needs these routine operations, such as making one. That would be a constructor in object-oriented programming languages. You have to create the data structure. Getters or setters, also known as accessors and mutators. These just allow you to look at data members and assign data members. Clearing a data structure means making it empty. And an iterator to loop through the elements of the data structure. Iterator is one way of doing that. There's other programming techniques, but basically a way to march through each element of the structure. These are pretty routine. We are going to talk about them, but they're not so exciting, so we don't usually focus on them so much in a class like this. The ones that are more interesting are things like inserting an element into a data structure. That often involves rearranging the elements in some way, or erasing an element, same thing. Searching for a particular value. One of the purposes of these structures is to make searching efficient, so we can do that in a clever way often. A little bit more about an invariant. An invariant is a rule that a structure has to obey all the time, and it's imposed by us when we design the structure in order to keep the data structure organized internally. So just for an example, we have introduced the concept of a unique pointer in C++, and there's an invariant on a unique pointer that it's a pointer that's either null to mean nothing, or it holds one valid dynamic object, and that's an invariant. So that rule means a unique pointer can't point at something else. It's not allowed to point at an invalid object. It's not allowed to point at a stack allocated object. The rule for unique pointer is it's either null, meaning nothing, empty, or it holds a valid dynamically allocated object. There can be structure-wide invariants. So that would be an invariant that applies to the whole structure. For example, if we have a sorted array as a data structure, it has to be in sorted order. That's the point of sorted array. So that would be an invariant that applies to the whole thing. And then we can also have invariants that apply to specific operations. So for example, an erase operation only works on a non-empty list. Erase means take one element out. Well, that doesn't work if the list is empty already. So there would be an invariant on an erase operation that says, I require that before you try to erase an element, you make sure that that list is not empty. And we often use the verb require or ensure for these. Every operation has to maintain all these invariants. So when we implement one of these operations, meaning write code for it, we have to be very careful that our code does not break any of these rules. Okay, a little bit about the notation we are going to be using for these abstract data types. We're going to be following along the notation of the Data Structures Wiki book. That's our main text. So what I'm going to do now is open up their abstract data type definition for the list, and we're going to look at that. Okay, so here we are. This is the data structures, list structures page in the data structures wiki book. And this part down here is the notation they use to describe the list. We're going to get into the list in a week or two. We're getting a little ahead, but I just want to show you an example of a description of an abstract data type. So they're saying a list given a item type. So this is kind of like a template type. There's a data type for each element. It's an ADT. And here's a description of one operation. So this here is the list of operations on a list. First operation is get begin. That's the name. And it takes no arguments because there's nothing between the parentheses. And the return type is a list iterator. And this returns a list iterator, we'll define that soon, that represents the first element of the list, runs in big O of one time. So this is defining that there's this operation on a list of getting an iterator that's at the beginning, and it takes constant time, big O of one. We're going to get to that soon enough. Maybe another example, prepend. So that's maybe an obscure English word, but that's why we have this description here that says adds a new element at the beginning of a list, runs in big O of one time. So this prepend operation takes a item of the appropriate type as input. There's nothing to the right here with a colon, so there's no return type. It's a void function, and it adds a new element at the beginning. That's what it does. And there's also a specification that it has to take big O of one time, which we'll get to soon enough. And it goes on. The list is longer. I don't see any data structure wide invariants here. So there's just operations, and some of the operations have their own invariants or rules. Okay, so that's it for abstract data types.